Crack Maxwell's equation step 2. This is a second video. You should watch the step 1 before you watch this one because it's a continuation. The Maxwell has one more equation, and I already explained in the first video. The Maxwell's Ampere's equation is J current generate B, and this equation is going to talk about B generate E and ultimately J. Okay, but this B is dynamic. It has to be derivative of time and negative in it. So as you see here, so the relationship between the this is a cause and this is the effect, the same equation, so we use the same math to say integral form is you take some surface, this is D, and calculate the B going through this circle. It's going to be same as line integral L, line integral of E, and it's going to be like the B alone doesn't generate anything. When B change over time, then E is generated. Which direction? Okay, the curl, so the B, if B is going this way, it should be right hand, but because of negative, okay, so when you have a B here, let's see, you have a B here and the B is changing over time negatively. So what's happened is you have to express this by vector. It could be this way, delta B, maybe negative, delta B is positive, whichever it may be over time, depend on this. So when B is increasing, so it's pointing this way, so the E is going to be generated by right hand rule this way when the B is increasing. A little bit more complicated, but it's the same thing. It's the curl always give right hand rule, so depend on which way this vector is pointing. Okay, if B is decreasing, then the decreasing positive this way, so the E is generated the other way around. Okay, now again, Maxwell's equation doesn't tell you two things. One, this is the cause, this is effect. That's one thing. And doesn't tell you how much E is generated by B. It doesn't tell you, right? So that's what we have to work on it, because B is going to generate, I mean the dynamic B, changing B generate E, but how much does it generate E? It's the same problem exists with Maxwell's another equation, Maxwell's Ampere's law. Okay, so since this change, magnetic field change, can be caused by either magnetic field moving or magnetic field changing. Changing means magnetic field gets stronger, weaker. Moving means like this magnetic stick moving around the conductance loop. So the B change, and direction of the E generated is orthogonal, but depend on whether B is increasing or decreasing. If decreasing, then use right hand rule. Okay, in this case it's decreasing. Decreasing means is positive, right? Okay, so why it's always orthogonal loop? Well, you examine this carefully, you will get this right hand rule for curl. And they used to teach right hand tool for magnetic and stuff, but actually that's confuse all student. I think right hand rule come from this mathematical equation. That's a way you need to understand so you don't get confused. So this is Maxwell. So what we are saying is that's fine. So J produce B, and B, the change, produce E, and this happen when J is changing, right? If J is time function, B is time function, then this time function derivative is going to produce E. So what happened is the voltage generated by this J's time function is going to be some kind of derivative. You can tell this, right? So that's the way the voltage is generated by magnetic field, which is generated by current. So current and voltage, there is a relationship in this conductance. Okay, that's what we talk about. So basically it's a negative feedback. If J flow this way, right, then B generated this way. If JT increase, then BT increase. So increase of B is going to is pointing this way. B this increase, that means we have to point down to figure out which ways the electrical field is generated. If you point down because negative, then E is generated this way, and this is countering J. Okay, and if you integrate E along this E, that's going to give a voltage. The voltage is countering the J. You need a J by applying a voltage original, but now you get counter voltage. So what does this mean? This resistance is called inductance. Okay, and what inductance means is when you have a current and that derivative is going to produce voltage across. If you have a conductor, it has to be alternate voltage. Okay, I, and that's gonna produce counter volume. Okay, now this counter volume caused by this is inductance. So voltage is di dt. So Maxwell's two equations lead to the definition of inductance. And if we calculate the inductance of many loops, A, area A, so and so, okay, so we can calculate exactly inductance is geometric parameter, just like a capacitance will have a geometric area A and distance L parameters. Okay, so inductance the same way. Maxwell's last two equation is going to define inductance. Okay, these details probably you never see in the electromagnetic textbook. So what does it mean? This, if you give sign, it's going to be derivative, so you have a phase shift, and this phase shift, the I V in the complex plane, phase shift is pi over 2, and that's why we write V equals J omega L I, and this is called impedance of inductance. Okay, so the J, you multiply J, so it's going to make a phase shift by pi over 2, and you have a omega in front here by derivatives, and the inductance constant, and that's going to be alternate current equation for inductance. Okay, it's everything connected, it's all come from Maxwell's equation, and I hope you understand at this level the connection between electric circuit and Maxwell's equation. It's all come from Maxwell's equation down to impedance definitions. Okay, I hope you enjoyed these videos. We have a step 3 now. When we have a feedback, the current generate magnetic field, and the magnetic field change generate current. What's happened? We combine two equations together to figure out what's going on in the field of magnetic and electrical effect. Okay, that's in a step 3. So if you like, please subscribe.